Okay, so we're going to look at how partial fractions work. This is a process in which we can take a complicated looking fraction and separate it out into simpler fractions with easier to work with denominators. It's sort of the reverse of finding a common denominator and combining them. We're going to undo that process. Now, this is particularly useful in calculus when you're trying to do integration. And so it's sometimes taught in pre-calculus courses because it's really just algebra. But it's algebra that you need in order to work with certain kinds of functions. So we're going to look at the sort of general properties, and then we're going to work through some examples. So to start with, we have to start with proper rational functions. In this case, we need the numerator to be a degree strictly less than the degree of the denominator. If you are trying to do partial fractions and that is not the case, then this won't work. So what you would have to do is you would have to simplify, and then do long division to get your, until you get your remainder, so that your numerator is strictly a smaller degree than the denominator. And then the leading terms that we're able to divide out, you don't have to worry about. They're already, manipulated. That's your oblique asymptote or whatever. And then the part that's left, you can apply partial fractions to. And typically, the other thing that we have to worry about in the algebra context is that the denominator has to be factorable. If the denominator is not factorable, in order to work with it in calculus, we'll need to do things like completing the square or things like that, but they won't necessarily yield to this idea of partial fractions. We have to actually be able to factor it in order to apply this technique. All right, so let's assume that both of those things are true. So we have an example here, like 3x plus 1 over x minus 2 and x plus 1. The denominator has a factor, has a leading term of x squared. The numerator has a leading term of x. So this does satisfy our proper fraction requirement. And what we would like to do is we would like to split this into two simpler fractions, a constant over one of the factors and a constant over the other factor. And so we're going to start out our partial fraction process by writing it in this way: some unknown constant over one factor plus some other unknown constant over the other factor. And if you have a bunch of linear factors like this that are not repeated, then you would do this for all of your individual factors. So if you had 3 factors, you would have A over the first factor and B over the second factor and C over the third factor, all as separate fractions. Now, if your linear factors are repeated, then, so let's say for this example, we have x minus 2 cubed, then we would actually have to have one separate term for each power leading up to the number of repetitions we have in our denominator. So A over x minus 2, 1 copy, B over x minus 2 squared, 2 copies, and then C over x minus 2 cubed, 3 copies, and then we would have D over whatever non-repeated linear factors remain. Now, in most textbooks, they will only give you multiplicity 2 problems just to check to make sure that you know how to do this. But in principle, if you had x minus 2 cubed, then you would have these 3 terms. Now, if you have quadratic factors and quadratic factors that are not factorable specifically, particularly those with complex roots, then what you're going to need to do is you're going to, instead of having just A over the quadratic factor, you will have to have a 1 degree less numerator. So a constant is 1 degree less than a linear factor, but in the quadratic case, you would need ax plus b over your quadratic factor. Now, if you are unlucky enough to get something that's not easily factorable, but has real roots, then you would have to, find the roots, find the real roots, use your quadratic formula or whatever, and you would have to write those as sort of messy, but otherwise real factors. So this technique specifically is for factors which actually have complex roots specifically. And so again, typically in most problems, they will be of the form where they're just the sum of squares, like in this case, but they don't have to be. If the roots are complex, you would still have to use the same technique. Now, when I say that this quadratic factor requires a linear numerator, that does not apply to repeated roots. Technically, if you were to combine all of these x minus 2 factors, you would have a cubic denominator, and then you would have a quadratic numerator. But it's disguised because we would then have to do additional math. If we were to try that technique, we'd have to do additional math to simplify it so that we can actually work with it. And we don't want to have to do that additional math after we've gone to the trouble of finding all these unknown constants. So if we set it up in this way, it actually does satisfy this linear over quadratic denominator collectively, but these will be easier for us to work with. It's sort of, we've teased out the algebra that we would have to do otherwise. And so this process will get us to something that we can work with much more quickly. So for quadratic factors, yes, you need the linear numerator, but that does not apply to repeated roots in the way that we're setting them up. And then it's also possible, of course, that you could end up with repeated quadratic factors. In textbook problems, these are somewhat uncommon, but conceivably it could happen. And in the case of repeated quadratic factors, then you would have this combination of, you would have one copy of the quadratic factor with a linear numerator, and then you would have your second copy. In this case, there's only multiplicity 2. So you'd have your second copy with the square, and then also the linear numerator. And again, I mean, technically together, you could combine these and you would have a 4th degree quadratic and you'd have a cubic numerator, but then you would have more work to do later when it came time to work with the thing. And so we don't set them up that way because we don't want to have to do additional algebra after we've done all of this math. So we set them up this way so that when we're finished, we actually get to a form that we can work with. All right, so again, we're always thinking in terms of these examples, in terms of getting them to a form that is conducive for us to continue doing calculus with. Even though if you're learning this in pre-calculus, I have no idea what you're talking about, and that's understandable. But there is a goal in mind. There is a reason that we set them up this way, and it has to do with calculus. All right, so let's look at some examples. So in this first example, we have 2 linear factors. One of them is repeated. This is if we were to follow it out, there's 3 factors in the denominator. So that's cubic, and then the numerator is squared. So that fits our proper fraction requirements. We're going to set this up. 1 linear factor, our copied linear factor, and then our second linear factor. And then what we have to do to solve this, there's a couple of different strategies, but essentially we have a system of linear equations, and sort of brute force way. There are some ways that you can get around this if you have lots of nice zeros. But basically the brute force way to do this is, once you have this set up, you find a common denominator. So let's look at, we want to get back to the original denominator we had. So for this A term, I would need to multiply by my missing x plus 5. And then for the B term, I need another copy of x minus 2 and a copy of x plus 5. And then for the C term, I'm missing my 2 copies of the x minus 2. And now all of my denominators are equal. And then what I essentially have to do is I have to multiply these out. Here I've FOILed out my x minus 2 and x plus 5. And here I FOILed out my x minus 2 squared. And then I distribute my a, b, and c. And so now what I'm going to do is I'm going to say, okay, so my denominators are the same. And so my numerator has to be the same as my old numerator. So I'm going to set up a system of linear equations whereby I'm going to pull out the coefficients essentially of my appropriate corresponding coefficients. So in this particular example, on the original numerator, I just had x squared, so it has a coefficient of 1. But in my sort of multiplied out form, I have two terms that have x squared in it, bx squared and cx squared. And so what I'm going to do is I'm going to say these have to be equal. These x squared components have to be equal, which means that whatever b and c are, they have to add together to be equal to 1. And so we do the same thing for the linear components. There are no linear components on the original original numerator. And so if we pull out our linear terms, we've got a, we've got 3bx, and we've got minus 4cx. Those have to be equal to 0. And again, if we basically divide out the x, we end up with a plus 3b minus 4c is equal to 0. And then we do the same thing for the constant. Our original numerator had a 4. And if we pull out the constants where there's no x's from our expression, we have our 5a, which is here. We have our 10b with negative 10b, which is here. And we have our 4c, which is here. And those have to all equal 4. So now we have 3 variables, 3 unknowns, 3 equations. B plus c is 1. A plus 3b minus 4c is 0, and 5a minus 10b plus 4c is equal to 4. Now, at this point, you have to figure out how to solve them. There's a bunch of different ways that you can do this. Obviously, you can do substitution. Let c be equal to 1 minus b. Plug it in everywhere, simplify, and then solve for, do your algebra. You can also do elimination. You can, feel free to switch modes. And at this point, what I did was I used elimination at the second step. I multiplied the top equation by 2, and then that allowed the b's to cancel, and that gave me 7a was equal to 8. And so I got a was equal to 8 over 7, and then I plugged in I plugged a into one of these equations to get b, and then I plugged my b in to one of these equations in order to get c. If you know how to use matrix operations, you can also do matrix operations in order to solve these problems. That also works just fine. The more variables you have, the more the matrix is like the way to go. But typically textbook problems, especially in the beginning of these examples, will try to make the variables work out nicely. And then they will start getting more complicated like this. Once we get to these solutions, we plug them back into the setup that we had up here. We would plug our a, b, and c into our expression in terms of those unknowns. Now, the other strategy that we have for solving these problems is that once we get our expression multiplied out, that numerator, we don't actually end up FOILing anything. We can save ourselves a little bit of work by choosing variables, choosing values for our coefficients for x that will eliminate some of the components and simplify our problem. So for instance, if I choose x is equal to 2, that's going to make my c term disappear. It's also going to make my b term disappear. And that's going to leave me with just the a term and the other side of the equation. So this all becomes 0. This becomes 0. On this side of the equation, I end up with 8. And on this side of the equation, I just end up with 7a, which is this 8/7 is exactly what I got earlier. Similarly, I can choose -5. -5, if I put it into this term, is going to make this go to 0. It's also going to make b go to 0. And then I'll just be left with this c term and stuff on the other side of the equation. So again, plugging it in, 0, 0, and then I get -7 squared. And then on this side of the equation, -5 squared plus 4. So this is going to be 49c. This is going to be 25 plus 4, which is 29. And I get c is 29/49. And then if I still have variables to solve, which will usually happen if you have repeated factors or if you have quadratics where you can't plug in something to make it 0, then you can choose other values like 0. 0 often works, and simplify your expression and then plug in the values of the variables you were able to find. That's usually going to be easier than like doing all the foiling that we did earlier. But this, if you plug in 0, you just recreate that constant equation that we had earlier, and then you can plug in the a value and the c value you found in this case in order to get the b value. Now, it just depends on what you're familiar with. The sort of first procedure that we found was sort of the typical way that this often gets taught. This is a little bit of a trick, but that doesn't necessarily always work. As you'll see, if you have, like I said, repeated factors, you may have more things that you have to worry about. And so you may not be able to solve for all of the coefficients. If there's no repetition, you'll be able to solve for all of the coefficients this way. But if you have lots of quadratic factors or things like that, then there's no way to eliminate them. They're not all 0. And so there's more variability on what can happen in this second procedure than the first procedure. But if you have a lot of variables, that initial procedure that we showed can kind of blow up a little bit. There can be a lot of foiling and things like that. And so sometimes I will use a combination of these techniques in order to get the answer in the most efficient way possible. But there are these different strategies for solving for these coefficients, but regardless of which of these two strategies that you use, you end up with the same result. And this is our final decomposition. And then we'll look at one more example that's going to involve a quadratic denominator. And again, we're going to separate it into two terms in this case, the linear term over the quadratic, and then our constant over the linear term that we have. And again, we're going to find our common denominator. That means we're going to need to multiply this expression by x minus 3 over x minus 3. And this one we'll have to multiply by x squared plus 1 over x squared plus 1. And that will get us this expression. And again, using our first method, we would FOIL all of this out. FOIL, 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 FOIL. We get this. And then we combine the coefficients for the individual components. So we have an x squared, a squared, x squared plus cx squared. There's no x squared over here, so that has to be equal to 0. So the x squareds cancel. For the linear terms, we have negative 3ax and bx. And so that has to be equal to 4 so that the x coefficients add up. And then for the constants, we have negative 3b and we have c, and that has to equal in this example to negative 7. And we can use our a plus c equals 0 so that we can say c is equal to negative a. Again, just using substitution, plug that in, and then we finish the algebra to get our remaining two constants. again, I use a combination of elimination and substitution. Now, for the second method, again, we find our common denominator, but we leave it in factored form. And I can start by guessing x is equal to 3. And that's going to eliminate all of these. And if I plug in x is equal to 3 on this side, I get 5 because this is 12 minus 7. And on this side, this all canceled, and I get c times 10. And so I get c is 1/2, which is the same thing I found before. 5 divided by 10 is 1/2. Now, since we can't make x squared plus 1 equal to 0, we just have to pick values for x. And then we can always use our c value to further simplify the expression. So if we choose x equals 0, that's going to eliminate the a from our expression because that's ax, so a times 0, that's going to go away. And so then we'll have b times -3 and c times 1, and then 4 times 0 minus 7. And so the -7 is left. We already know what c is. We can substitute that in, and then we can use that in order to solve for b. And we end up with the same 5/2 that we found earlier. And then you just keep doing this, usually with small values, until you find all of your coefficients. Let's say we say x is equal to 1. That will preserve the a, but we already know what b and c are. So now it's just a matter of plugging in, simplifying the equation, plugging in our values for b and c, and then getting a by itself. And we get the -1/2 that we had earlier. And so finally, we end up with this expression. And typically, when we would integrate this, we'd actually split this, and we would have some coefficient in x over the quadratic term, and our coefficient times the constant over our quadratic term, and then our coefficient and the constant over our linear term. Now, occasionally, you will be asked problems that are not actually asking you to solve all of these coefficients. Most of the problems where you're asked to solve for coefficients will not actually go further than solving for 3 coefficients, because as you can see, the algebra can be quite time consuming. But you may get tested on some of these general properties. And actually, these are kinds of questions that I sometimes like to ask. We talked about what happens if you have repeated quadratic terms, or what if you have repeated linear terms, or you have some combination of repeated linear, non-repeated linear, repeated quadratic, non-repeated quadratic. How would you set those up? And so that's something to kind of keep in mind. You still need to know all of these separate rules and how to apply them in combination. Setting up a more complex factoring experiment where you have lots of factors in your denominator, typically you're not meant to actually solve all of those. That's what technology is for. But you may be asked to set up the decomposition, and remembering that if you have the multiplicity 3, then you have to make it 3 times, with each factor increasing by a degree of 1, and then the repeated quadratic factors and so forth. And so sometimes I've seen problems where students will be asked to set up a problem that ends up with as many as 11 different coefficients to solve for. But then the idea is that you actually don't solve for those. You just set up the form. And so an example would be something like this example 10 right here, example X. We have a repeated quadratic factor, we have a repeated linear factor, and then we have 2 separate linear factors. And so how would you set these up? You would have your one-time copy, ax plus b over x squared plus 1. And then you would have your multiplicity cx plus d over x squared plus 1 squared. And then you would have your repeated linear copies. So you would have, we're up to d over x minus 3. And then f, we're up to f now, f over x minus 3 squared. And then g over x minus 3 cubed. And then you would have h over x plus 4 and I over x minus 1. And then you would just stop. Because again, that's 9 variables. I think that's 9 variables. And yeah, 9 variables. And so that's a lot to solve for, and that's not really the purpose. The purpose of some of these more complex problems is simply to see that you know how to set them up correctly, and then you would let technology solve the problems. For what kind of form would you be expecting? Sometimes in calculus, you might be asked to do the integration and just leave the ABCDs, whatever, as they are. And then again, technology can solve for them later. What does the form look like? But most of the time, if you're asked to solve for the coefficients, they will be relatively more straightforward, where you're only applying sort of one of these different, or two, maybe two at most of these different scenarios, not all 4 of them simultaneously.